Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Good evening, everybody. Guys, how are you today? So, hopefully today is your day. You are in the good conditions. Okay. So, let's continue our class. But today I not giving the lecture, but I will show you some uh, of the problem and answer of the example for chapter number 3. That's it, which is first law of thermodynamics. But we are focusing on the open system or control volume system, or in other words is for the equations of SFEE, steady flow energy equations. Okay, so me share the let me share the question. So actually the question is from final exam question for the thermodynamics, code MEC 450 or 451, but also we can use it as a reference to study in our thermodynamics MEM 462. So this is a final exam question, January, okay, January 2019. So, guys, you can download this question from the libraries, PTAR libraries. So just go in the past exam questions, and then from there you can download. Okay. Okay, let's go straight to the example of this question number 2B. Okay, this question is about, as I mentioned, this is about the first law, steady flow energy equations. Why why I know? Okay, how do I know this is for the SFEE application application question? So as you see in the question, it said determine. Okay, determine the velocity at the exit of the diffuser when CO2 at 105 kilopascal and 300 kelvins enters it with a velocity of 380 meter per second, and the exit state is 225 kilopascal and 370 Kelvin with specific heat loss of approximately 5 kilojoule per kilogram. Okay, based on this sentence, you will see that the sentence mention diffusal. Okay, as you know, diffusers you must know, not as you know, you must know. You must imagine, and also you know how the pictures of diffuser. Okay, diffuser have uh, inlet and exit. So when it have inlet and exit, it is categorized in open system, where the mass can go across the boundary. So this question is about the open system. So now it want you to determine the velocity. Okay. So for the velocity, we know that in chapter number 3, first law, using focusing on the open system, we have equations named SFEE, where the equation is Q minus W is equals to delta H plus delta kinetic energy plus delta potential energy. And this equation actually come from Q minus W is equal to delta E, okay, where the energy, the total difference changes of energy is including enthalpy, potential energy, kinetic energy, and also potential and kinetic energy. Okay, so what you what firstly what you should do when you get this question. Okay, firstly list down what has been given. Okay, this is the diffusal. Okay, the schematic diagram of the diffusal. So inlet, we put all the values that has been given in the questions, and also this diffusal use or the working fluid that been used by this diffusal is carbon dioxide. That's mean a gas. So when the working fluid is a gas, so the simplest way to solve this problem is using the method or the using the method of ideal gas approach. Okay, so you have to use the equations of the ideal gas. Okay, that is the one of the simplest how you want to solve these problems. Okay, so uh, it show all the values here. Okay, so we start for the energy balance equations for the diffuser. H1 plus KE kinetic energy is equal to Q out plus H2 plus KE. Okay, what is this equations energy balance come from? Okay, I will show you. Mm, um, okay, actually, this equation come from uh, Q minus W is equals to theta E. Okay, to big. So Q minus W is equals to when we calculate for the open system, we have to consider the force that pushing the working fluid, the kinetic energy, the potential energy. And this force pushing the working fluid can be converted or easily changed to the enthalpy. That's mean the change of enthalpy plus the change of kinetic energy plus the changes of potential energy. So in this case of diffusal, what we have to ignore, okay, ignore work because there was no work in the diffusal, and also uh, there is no, or we neglect potential energy. But kinetic energy we do not neglect because in this question it mentioned that the velocity inlet and outlet, it have a velocity at the inlet. Okay, so that's why we don't neglect potential energy, kinetic energy, because from the kinetic energy we can find the uh, velocity. Okay, enthalpy. Okay, we have to find the enthalpy, but Q here, it not mention the diffuser is adiabatic, but although we know that the diffuser can be assumed as an adiabatic process, but in this case, it's mentioned that it have a heat loss about 5 kilojoule per kg. So for when it have a heat loss, you have to put Q out here. So Q out, uh, Q in is equal to 0 because there was Q in, it not mentioned in this problem. So it's equals to delta H, or I simplify H2 minus H1 plus over 2 C square, or in this use K, okay, I use it K E, 2 minus K E1. Okay, so we rearrange these equations, then it will got this equation. Okay, H1, uh, so okay, but please remember, you have to put negative as a Q out loss, because this calculation I follow from Chengel Alter books. Okay, so if we follow or we for use the approach of the Chengel, what must we consider? Okay, what must we consider? All right, properties table, because Chengel, I want to show, because okay, because you have to remember when you use Chengel, that means this is a system. Okay, system work, uh, work in, work out, Q out, Q in. Okay, Chengel said when work is out, the signation is positive. When work is in, the signation is negative. Okay, same as the Q out. When the Q out heat out, the signation of this Q out from this system, the signation is negative. Q in is positive. This is the signations that you have to remember when you want to solve the thermodynamics solutions. Okay, so that's why Q out is negative. So from here, okay, from here, we want to find H1. H1, actually using the ideal gas assumptions, we know that from the assumption, the formula of Cp is equal to delta H over delta T. So this is how can we find H1. Okay, H1 is equals to Cpt. Okay, for state number 1, T has been given in the equation, also Cp. So we get the answer of H1. Ke is C1 or V1 powered by 2, V1 squared, V1 powered by 2 over 200. That means, so we put 380 over 2000. So we get the potential energy, okay, in unit, okay, in unit kilojoule per kg. Okay, next is H2. Also use the formula of Cp. So H2 is equal to Cpt. Then we get the values. Then K2 using the equations from the diffusal that have been defined first earlier here. So from there we can get kinetic energy at state number 2 at the exit. So the value that come out from the calculations is 7.898 kilojoule per kg. That is the kinetic energy. Okay, kinetic energy produced because of the velocity. So it got the velocity. So rearrange for the velocity. We because this question we want you to find the velocity of the diffusal, the velocity or exit of the diffusal. So we know the formula for kinetic energy is Ke is equals to half c square. Okay, so from here, um, rearrange the formula to get the C. That means C is V. In here, in the solution, it term as V. So lastly, you will get V is 126.33. Okay. Another thing that you don't make it difficult. Don't make it quite difficult because of the 2000. Okay, why it put 2000 not 2? Okay, actually 2000 is because it want to change the unit kilojoule. Okay, kilojoule here, it want to terminate k here, so to get the unit of meter per second. That's why. Okay. um, that is for the first example. Any question, guys? Okay, no. So can I continue? All right. Okay, thank you. Okay, we continue. So the next one, question number 2, C. Okay, this is also about the uh, open system. How do I know this is open system? Okay, we look at the sentence that it mentions that mixing chamber. So the mixing chamber have an inlet and also have outlet. So of course this is mass can go to the boundary. So go in and come out. That's why it's called an open system. And the working fluid that used here is water. Water. So when we see water, so what happened? What we have to remember? So the solutions must use properties table. Okay, because the water. That is some simplest way to do this calculation. Use the properties way. Okay. So, okay, let's read the examples to see. Consider an ideal adiabatic mixture chamber. So this chamber is adiabatic. That means heat Q is 0 with 2 inlet and 1 outlet. Cool water at 25 Celsius enters inlet number 1 and superheated steam at 250 Celsius enter inlet number 2. Okay, that's mean that the working fluid here is water. Water may be in the phase of a mixture or liquid, but another water are in the is in the phase of steam or vapor. Okay, superheated steam. Okay, uh, then it says if the mixture leave the mixing chamber, that means outlet number 3 at 320 bar with a moisture content of 25%, determine the ratio Y of the mass flow rate of the cool water and superheated steam. Okay, so how to solve this question? Seperti biasa, as usual, you have to draw, okay, the schematic diagram or a picture that for you to understand more. Okay, this is a mixing chamber. So number two is steam, number one is water mixed together, and then come to number three. Okay, so then based on the energy balance equations, as I mentioned earlier, Q in minus Q out is equal to E system. So for open system, um, uh, energy in is equal to energy out. Okay, energy in is equal to energy out. So for ideal adiabatic mixing chamber with two inlet and one outlet, okay, when we put together, that's mean all thing here, Q minus W is equals to that H plus that kinetic energy plus that PE. Okay, what happened here? Lastly, the ideal adiabatic mixing chamber with two inlet will become like for equation number one. For adiabatic mixing chamber is two inlet, so we know that in, okay, energy in is equal to energy out. So energy in is m dot h m dot 2 plus n dot 2 is equals to m dot 3 h3. That is for energy in is equal to energy out. Okay. But for the mass balance for typical mixing chamber, okay, for mass balance for typical mixing chamber, M3 is equals to M1 plus M2 dot. Okay, so substituting equation 2 into 1, okay, what happened? It will give equation number 3. Okay, and then we know that the ratio Y of the mass flow rate of the cool water of superheated water is cool over superheated is Y. So divided equation 3 into m dot 2, then it will become y h1 plus h is equal to y h3 plus h3. So rearrange, we got is equals to h3 minus h2 over h1 minus h3. Okay. Okay. This is the equations that we have to find the value of y. Okay. Based on the value that I have given in the question, state number one. So I mentioned earlier, this is the solution based on the properties table. So state one, you have two properties because once you want to look on the properties table, you have to know at least two properties. So state 120, 1 to 100 kilopascal, and the temperature is 25 Celsius. So at these conditions, we look on the properties tables. Okay, go for the saturated water. Saturated water. Okay, saturated water table. Find 120, 1225. 1225. 1200 kilopascal. The temperature, saturated temperature is 187. Okay, 187. So the temperature mentioned in the question is 25. That's mean T1 that mentioned in the question if below than T saturated, then the state number one is a compressed liquid. Okay, compressed liquid. So when it compressed liquid, H1 is equal to HF. So you just state number two, using two properties that has been mentioned in the questions. Uh, compare T2 250 with T saturated at 120 kilopascal. So then when you compare it, it show that T2 is bigger. Okay, is bigger than T saturated. So it is superheated region. So look on the superheated region tables. Then from there you will find H2 is 2935.6 kilojoule per kg. So where to find superheated region? So using the properties table, go for superheated region, superheated water. Okay, find 120, 1.1, 1.2 megapascal. Okay, 1.2 megapascal. The temperature is 250. So H29 2935. Okay, 2935. 2935.6 kilojoule. That is H2. Okay. For state number 3, uh, it mentioned that at state number 3, it had a moisture content of 25%. So this state 3 is a mixture region because this question mentioned that state 3 is have moisture content 25%. So we confirm this is a mixture region. So when we know this is a mixture region, just using the formula H3 is equals to HF plus at HFG. Then from there, at 1,200 kilopascal at saturated water, find HF and also HFG, and then you will get H3. Okay, the value of H3. Therefore, from all these value H1, H2, and H3, put together to find y, and then lastly it will give y is equal to 0.297. That is the answer for question number uh, 2C. So these two examples is basically based on the SFEE steady flow energy equations. So please do the exercise more, and please study back these examples, and then keep doing and keep understanding how it works. Okay. So anything you want to ask, guys? No. All right. Okay, thank you very much. That's all for today. So have a nice day. So see you in next class. Okay, Assalamualaikum warahmatullahi wabarakatuh, and uh, be whatever you are. Thank you.